Now a postdoctoral researcher at Luleå Technical University, Sweden. So tomorrow is my period getting end. So almost I have finished with all my work and I'll be joining as assistant professor here at NITTTR, National Institute for Technical Teachers Training and Research. The topic which we are going to see today is power quality issues of EV integration with the grid. That is the electric vehicle integration with the grid. So coming about me, giving a small introduction to me, I was born in Kerala, brought up there in Tamil Nadu. I did all my studies there. After marriage, I came to Chandigarh and I joined NITTTR, National Institute for Technical Teachers Training and Research, and I was working as assistant professor. At the same time, I finished my PhD from Punjab Engineering College, PEC, now the deemed university. And after that, I got an opportunity to go to Sweden and do my postdoc. So for a 2 years period, and I'm completing it tomorrow. So last 2 weeks, I am back here, and this was the research area was in electrical power engineering, and I was doing it in the energy science department of engineering science and mathematics. And this was a team at Luleå University of Technology at the electrical power engineering, and Professor Matt Bolin, he is the one who was guiding us, and all these are PhD students. And this is an extension campus at Skelleftea, which was around 2 hours distance from the main campus. So this is only a research center where they do research. So the main research done by this electrical team is on power quality, low and medium voltage distribution, electricity market, transmission system reliability, and electromobility. So I was taken for this project on electromobility with power quality. So some power quality issues I had to study based on the electromobility. So here, if you see, whenever we talk about electric vehicle, when an electric vehicle starts charging, some light flicker can be seen in the nearby LEDs or lamps connected. So that's one of the big problem which was seen in Sweden also. In many places, when people started charging, they could see that in the garage itself the light is blinking. Apart from that, in a study done by Horstman in Netherlands, what he saw is it was a study done in an industry where they were producing paper products to avoid plastic. They were going for recycling the paper and doing some products out of it. In that, there were 3 PV power plants which were around 220 kilowatt, 350 amps, 3 such plants with 10 EVs charging stations present. And when this EV PV combinations are there, it was seen that during a particular period, that is from 12 o'clock to 2 o'clock, when the PV production was very high, they could see some harmonics, like 11th and 13th harmonics was high, and they were jumping. They were not constant, they were going on changing. So that was due to some interaction. And when they analyzed it, they found that it was due to the EV which was charging, its switching frequency, and the PV inverter switching frequency. They interacted with each other and they created these harmonics, which was the lower order harmonics there. So here also, this is Cochin Airport, which I can see, and here which I have shown here on the left corner, and you can see here the parking lots fully with PV. So in India also in future we expect that all the vehicles will be converted into EV. In that case, what happens? The EV charging station will be given by these solar panels. So compared to the population in Sweden and other places, here the number of vehicles also will be more getting charged at the same time. So such phenomenons can be seen here in a different format. Like from place to place it differs because the grid impedance, it depends on many factors how it varies. So compared to the Indian condition, more extreme power quality issues can be seen. And the other issue in Sweden which we saw is there all the buses are electric. Now they have converted all the buses to electric. That's a project which is going on, trying to convert all, and many of these cities they have converted into electric buses. And here you can see, I think you can see my cursor. Here there is a transformer house behind small one and that in that house the transformers are there for both the bus as well as these are some of the customers nearby. And this is an ABB converter, and this is a pentagram that is used for charging this bus. And now the study which they are going to carry on is the study is yet to be done. They have got some scholarship for this, so they will appoint some student and they will start. The main thing is when this bus will start charging. So bus is around 300 kilowatt charger, and 300 kilowatt charger, and the amps are also 300 and around 500 amps at same instant it will be drawing. So when such high current is drawn, what will be the effect on will there be any power quality issues in the nearby houses? So that is one type of study which is in progress. Another thing is whenever the electric vehicles are charging, in India also you can see there are extreme climates like from down south to the tops north. Winters and summer, like hot summers are there. So the batteries get discharged. So that's also a problem. When the battery gives maximum efficiency, battery's maximum efficiency is at 20 degrees C. Okay, it will give the maximum output. But when it is 40 or 30, or if it is minus 40 or minus 30, it's just like a U curve. What happens is the efficiency decreases. It gets discharged faster. So in summer, extreme summer or in winter, you have to charge the battery more time than at a normal climate of 20 degrees. You would have faced this in when if you are in a region where it is extreme winters, you have to charge your mobiles also very often than in summer. If you would have noticed, you would have found that the batteries get discharged faster in winter. So this phenomenon also, like when the battery, like if Nissan Leaf or any company they give so many kilometers, but based on the climate also it changes. So what happens? The number of EVs in winters, if the batteries are getting discharged, what will happen if they're in an area if there are 100 cars and the battery is discharging faster? More number of cars will go and get connected to the grid than on the same, say if on one day if 50 cars are getting connected for charging, in summer it may be only 25 cars. Because in summer, the number of, in summer, this is not extreme summer, in say around 20 degrees or 25 degrees, it will be normal. So number of cars charging will be less. So when more number of cars are charging in the grid, again, power quality issues may come in the grid. So many such problems are still there, which can be analyzed. So coming to like for those who don't know about the EV chargers, there are different EV chargers, level 1, level 2 chargers, level 3, or sometimes in some norms they say it as type A, type B, type C. And this Chadimo is a type of charger. That is also, that's a Japanese charger, which means when you can have a tea while charging. So that is Chadimo. So that's a very common charger which is seen in all the places. That's a DC charger. So level 1 chargers are the chargers which are used in our houses, like a single phase charger you can say. Level 2, again, yeah, public places it is used, 20 kilowatt. It is little faster, but in order to understand this still easy, let me put it in this way, charging levels. So you can have it as single phase chargers or 3-phase chargers or DC chargers. Single phase chargers, according to my thing, when I was doing research, I was even telling my professor that might be in future, maybe a single phase 16 amps charger. Because say nowadays, we also, when a mobile get discharged, we want to charge it at our home itself. So same way, people will also prefer that they charge their mobile, charge their car also at their home after work when they come, or in the nights they can put it for charging. But the problem will be that it will take a long time. But many times we don't worry about it. Say we put it before going to sleep, and morning, or might be auto cut is there around 4 or 5 hours it will take, and morning it will be fully charged. So we are not worried about paying more and going and getting it charged outside. If this is, or if the current, like, because in our house also more than 16 amps point will not be there. So 32 amps might be, it's in a public place only. In private, in houses, I don't think so we'll be able to do this. So it's a 7.4 kilowatt single phase charger, but it charges, like you can see the charging time, when the amps rating is high, it takes only 2 to 2.5 hours. 3-phase chargers are there, 11 kilowatt, 22 kilowatt and 43 kilowatt. The only difference there in the 3-phase is the amps again, 16, 32 and 63 amps. So again, the time, if it is a 16 amp 3-phase, 2 hours if it takes. For a 3-phase 32 amps, it takes only 50 minutes. And for a 3-phase 63 amps, it takes 20 minutes. So if you come for DC charging, that's the one which is preferred in Sweden. Also, in many places we saw when we took measurements, it was a DC charger. So they are very fast chargers and more efficient. And like this 50 kilowatts, 120 kilowatts are some of the chargers which takes only 20 minutes or some 10 minutes. So if you want to do this, like the research which we were trying to do in India as well as in Sweden was very different. Here in India also I was trying to work with electric vehicles. We made some small models. We were trying to create some inverters. We made a prototype of the whole, or we made an auto rickshaw, we can say, an electric vehicle fully with batteries and all these things. I was working. So I was thinking might be I'll be going and doing such a research there when I got selected, but it was very different. There the research is very different. There they do it with real time. When chargers are already there in the market, they say now identify what are the problems which these chargers are creating. So such type of research is going on there. So in that case, what we did is you have the grid, you have some fast chargers and electric vehicles are coming and charging. At the PCC of this, that is the common point of coupling in the distribution board. We just go put the power quality meter, we analyze, we take all the data of all these cars getting charged, and then we analyze and we see what are the problems that can be expected. The main thing what they want is what unknown problems can exist. That is the thing. So some of the problems which we identified, I can tell you. The main reason for this is setting standards. You would have come across the IEEE standards for power quality for all the harmonics. The third harmonics, the limit should be less. THD should be less than 5% when you're connecting it to the grid. So individual harmonics should be less than 3%. So we have some limits. Similarly, there are many other problems which can come. So limits have to be set, or we can say it as the immunity standards, immunity for each device. If somebody is manufacturing an inverter, we have to tell that manufacturer that these things rating or value should be between this. Otherwise, we will not allow you to put your product in the grid or sell it. So in such places, standards have to be set. So now we have to find for already existing things, okay, is there any new problem coming? Should we give some standards? So for that, they do many research and they try to give some limits or for these immunity limits or setting up standards. In these places, they help. They identify which are the equipments which are creating problems, which are the ones which have to be rectified. And all these power quality issues, they analyze. So that is what it is done. But I was just thinking, like, can that research be done in India? So in India, maybe the number of chargers are very less. So, and getting a permission to go and take real-time data will also be very difficult. So one possibility is, I think in all the institute we have hardware and loop systems where the grid can be simulated, real-time simulators, and we have the device under test with the amplifier. So you can have here a power converter or any microgrid switch or battery system or a drive or anything connected here, connected to the grid, and with the power amplifier you can exchange power. Okay, you can amplify it and get it out, control this, and now you can study what are the power quality issues there. So this is a possibility for hardware in loop systems. You have many systems. You have DSpace based systems, Opal RT, Typhoon Hill, and I think your institute also has all these things. So if somebody is interested in doing such research, you can go for these hardware and loop systems. So when now an electric vehicle is there, you're connecting it to the grid, what are the problems you can expect? So these are the topics which we did research. I was coordinating this project, so being the postdoc student, and many PhD students were under me who were doing in different topics. Some were working with under voltage, over voltage, unbalanced, harmonic and all. So slightly I'll cover with all these topics. I have given you 2 reports which I have sent. In that detailed study, what they have done, detailed with all the analysis and the models, everything is done. So if somebody is interested in one specific thing, you can go and read there. Okay, so now first is the under voltage. So coming to under voltage, this uh, this EV charger, this charger, if you see, it's a load. When you connect to the grid, it's a load. So it consumes active power and might be a little of reactive power. And this active power, what happens is, say you're connecting it to the line, it results in some slight voltage drop. So how much voltage will drop? It depends on many factors. One is the rating of the device. Is it a 16 amp device or is it a 150 amps device? So it depends on the rating of the device. Second, it depends on the impedance of the grid. The grid will have an impedance. Okay, so based on that, because voltage is current into this impedance. If it is a strong grid, the voltage drop will be very less. You will not know it also. If it is a weak grid, then there will be a large voltage drop and that impact can be seen in the grid. So since you are BTech students, I can tell you what is a weak grid or a thing. Say cables are there, maybe underground overhead lines, and weak grid in the sense, say from the transformer, these points are far away. For example, a rural area you take, you have a transformer and these wires are very long and houses are very far. So long cables or long overhead lines will go. So what happens in that case, the impedance will be high. So in that case, the voltage drop will be high at the other end. But in mostly cities, if you see, in each street you have a transformer and you get the houses are nearby, so the length of the cable and other things. So in that case, when you measure the impedance will be very less, some 0.02 ohm or something. In that case, the voltage drop will be very less. So in this case, under voltage, as I told you, it depends whether the impedance of the grid as well as what is the charger size. Over voltage, it is just same thing. Say in which, if it is a three-phase line and in one line, single phase, you are using a single phase charger, you're connecting it in one, there will be a small voltage. If it is a weak grid, there will be a voltage drop in that. But in the other two phase or in maybe one of the phase, there will be a slight voltage rise. And now you can see that if you are connecting a PV, okay, if you are connecting a PV to this, if it is a single phase PV, what will happen? PV is just opposite to the EV, electric vehicle. To the phase where you have connected the PV, the photovoltaic, there it's a generator. So what happens there? The voltage will increase. Okay, to the phase where you're connecting, the voltage will be slightly higher than this. So what happens there and over, and you're connecting a EV, and what happens on the other phase, you're connected a PV, so over voltage may occur. So such studies are on phase only. Many of them are many studies are going on. There are no concrete papers on it. So, but the group is also doing many research that whether this combination can create problem. Similarly, unbalance. That is, unbalance is nothing but the ratio of negative sequence to the positive sequence voltage, and as per the standards, the value should not go above 2%. So if it goes above 2%, unbalance will be created. So this EV-PV combination may also create unbalance. And in future, let us think that in a street, like many houses are there and all are going to charge their EV. And PV, like many of the houses in Chandigarh and all, it is compulsory that your house has so many square feet, you should have a PV panel in your house. So such combinations can come which may create problems. So such problems are also there. Harmonics, yes. Then this charger, it is AC, and then you have to convert to DC. So a rectifier is there. Whenever a rectifier is there, again you will have harmonics. If it's a single phase, third and fifth harmonics will be dominant. If it's a three phase, again 5, 7, all these harmonics. Again, it depends on the type of converter used there. It's a 6 pulse or 12 pulse. 6 pulse, then 5 and 7 will be high. Or if it is a 12 pulse, 11 and 13 will be high. So these combinations, so these harmonics will be injected into the grid. Injected into the grid, or it may be to your neighbors. If it is in the distributed system, it may get injected. Apart from that, something called interharmonics. I think many of you didn't have heard about, or some would have learned this interharmonics. Interharmonics are harmonics which are not the integer multiple. For example, for harmonics, if you see, you have even harmonics like 2, 4, 6, and odd harmonics 3, 7. Like that, you have the odd harmonics. But interharmonics are those which are less than 2 kilohertz. That is the lower order harmonics, but they are not the integer multiple. Like it may be some uh, like 3.7, 11.8. So these are said to be the interharmonics, which are not the integer multiples. Okay, so these interharmonics are also seen in these when these EVs are charging. That I'll be showing you in some measurement. Then supraharmonics. This was a word coined by Professor Matt and Sarah Ronberg. They are my guides. So this phenomenon was identified by them, and it was published. So now the group is mainly working on the supraharmonics. This supraharmonics is in power electronics, if you would have come across. For lower order harmonics, we say till 2 kilohertz, and higher order harmonics starts from 150 kilohertz and high. They have never, like in IEEE and IEC, they had not given any standards between 2 kilohertz and 150 kilohertz, because before those when the power electronics came, also it was the switching frequency and everything was in the lower order or in the higher order, mostly not in this range. But now you can see that many manufacturers, and in power line communication, this range was there. So some of the things were, like some of the standards were defined for those periods. But now, what happened is when the electric vehicle and other things came, their switching frequencies can be seen in this 2 kilohertz to 150 kilohertz. In our measurement, also we saw that. So this is a common problem which is seen. Then you have fast voltage variation. When EVs are charging, very fast voltage variations can be seen. That is due to compatibility check, insulation test, or onboard battery protection, voltage checks, CAN communication checks, all these things. And because of these fast voltage variations, light flickers can also be seen. So that I'll be showing you why these light flickers are coming. So this was a measurement we did with an ABB charger, and it was a 175 kilohertz, 375 amps charger. So this around for 30 days we measured it for 1 month, and 90 cycles we got, like 90 different charging cycles. So this is a fast charger as a DC fast charger of ABB. And you can see here different vehicles. So this is like each charging around 90 cycles are there. That is expanded here down. So you can see here, this is one vehicle getting charged. This is another vehicle. This is another vehicle. So when different vehicles come and charge, they have different patterns. Okay, so this was a electric vehicle testing center. So these vehicles are the vehicles which have not come in the market. So usually all the companies, when they manufacture it, they go for hard testing before bringing it to the market. So these are some of the latest cars which have not come in the market. This was taken like around in the third month, like this year, the third month it was taken. March. So these vehicles might be coming out now. So these are some of the vehicles whose power electronics status is not known out. So from this we can analyze what are the power quality issues there, but we will not know what type of power electronics is used inside the car or inside the grid. That status is not known to us. And here you can see different cycles, and some like say some cars has taken only 50 amps, some have taken 200 amps. So since I said this is a fast charger, if a car take more current, it charges faster. Again, it depends on the state of charge of the vehicle also. If the vehicle is fully charged, it takes only very less time. But if it is a car which has a capability to charge at a very high rate, then it gets charged since it faster, since it's a fast charger. So these were the different patterns which we identified, and the third harmonics of all the cars, around 90 cars charging. So we found that it's not only the background harmonics, during charging also these harmonics are there. This is the fifth harmonics, this is the seventh harmonic, these are some of the 11th harmonics. So this is one of the car which was charging with around 50 kilowatt. Fast charging, it took only some 15 to 20 minutes. Another car which charged, it took 1.5 an hour I think, and it was only 11 kilowatt charging. So for the same charger, different cars can charge, but based on the car's capability, the charging time differs. And this was the thing which I wanted to show you, like say harmonics. When the car started charging and when the car stopped charging, the harmonics are very high. Similarly, the interharmonics also, you can see. So interharmonics also are high when there is a transient. Whenever there is a transient change, you can see the interharmonics are high. In this case also you can see here a small dip like here. So interharmonics and harmonic values. Similarly, these are different car patterns. So these are the same like similar type of car with different state of charge. Like this car might be with this high state of charge, that's why it charged for less time. This state of charge was very less, maybe 20% charge, then it will take a long time for charging. So these are also different patterns which we identified. This also has two similar cars. These are different patterns. And we tried to find the impedance of the grid. So that was a strong grid. So this is for the strong grid, the yellow line and red line, the calculated and the actual one. And we found that it was, if we imagine that it was a weak grid, in that case you can see large voltage drops like this. And the harmonic profile for all those 94 charging cycles was taken, and was found that the harmonic, 5th harmonic, 7th harmonic, 11th, 17th, 23th, these harmonics were high, more than 1% of the rated value. Even the 4th harmonics was high. So we were interested in knowing that why this even harmonics was high. Is there any imbalance in this circuit, or that had to be analyzed. So these things were studied. This was the interharmonics. Interharmonics was found whenever there is a transience, it was high. So such studies, like now the study is when multiple cars, this is only one car charging, when multiple cars charge, whether these will get aggregated and create any amplification, like get amplified due to resonance in the grid. So such problem can occur in the grid. So is it possible? So such studies are also done. Another thing is said to be the supraharmonics, which I was telling, which was coined by our group. So there, supraharmonics are the harmonics between 2 kilohertz and 150 kilohertz. And this was some experimentation done in our laboratory. Electric vehicle was tested, and this car, it was a 6 kilohertz switching frequency. So this was a EV current in the time domain. This is in the frequency domain. In this time frequency domain, that's the spectrogram. And at the PCC, they could see that same 6 kilohertz. But apart from that, there was 100 kilohertz. That was found in all the cars, which around 4 or 5 cars were tested, and this was found in all the cars. So it was something from the laboratory itself and not because of the electric vehicle. And in the neutral and protective earth also, this 6 kilohertz component was seen. So this when it goes through the neutral and protective earth, this may result in unnecessary tripping of RCD. So that study was also done. This was another car. Which had a broad band of switching frequency between 45 to 50 kilohertz. You can see that here, the EV, similarly in the neutral and protective earth, and modulated version was found in the PC. So some modulation, 180 degree shift was found, modulated thing was present in the PCC. So like again, this person who brought this car had a problem that whenever he was charging this car in his house, his in the garage, his light was also flickering. So this more analysis was done with this. Similarly, so supraharmonic with the same car, they did some analysis like when it goes to the neutral or protective earth, is there any chance of RCD tripping? So that yeah, it was creating a magnetic force which was enough to trip. Like this is the line for tripping, so it was going beyond this line, which means that tripping of unnecessary tripping, like or unwanted tripping of RCD may occur. Another study was on light flicker, so on LED. So what they did is they took the LED and the rectifier portion. This is the original diode conduction period. Now what they did, this supraharmonics, they superimposed on this. 3 volt super harmonics was superimposed. So superharmonics, I said, it's a harmonic range between 2 kilohertz to 150. So here they took 12.5 kilohertz and they superimposed on it. And now the modulation depth is seen here. And here you can see this is the permanent conduction of the diode. This was the intermittent conduction period, and this is the intermittent conduction period and the blocking period. For the same diode, what they did, they increased the superharmonic to 7 volt. So what they found is this permanent conduction period got reduced and the intermittent conduction period also increased. This means that diode is conducting only for a short period. So what happens automatically, the output also will reduce and the LED will start flickering. So that was the reason why the LED was flickering. That was proved by this paper by Selchuk, who is our team member, and this got published in IEEE Transaction of Power Electronics. And after this, he has two more papers in power electronics, IEEE Transaction Power Electronics, where he has found the immunity limit for these devices, like how much these superharmonics can be emitted, so that it is within the limit. Another problem that superharmonics can create is hearing problem, because say human beings can hear from 20 hertz to around 17. The adult can hear some 17 kilohertz. But babies or old people can hear till 20 kilohertz. So you just think if there is a 20 kilohertz frequency component in the EV charging, so, and a baby is there inside the car, we might not hear, but baby will start crying. And even say if it is a 40 kilohertz, dogs can hear. So dogs get irritated and they may bite. So such problems can come. So for that, immunity limits have to be set for each device. So that's why the group is working on to find what should be the limit that these equipments or these devices can emit into the grid. So these limits are not set in IEEE or IEC standards for these supraharmonics and interharmonics. So in order to set these limits, some standards are required. So some proper testings are required, and to find like what are the permissible limits, because these things are new things which are coming into the market. So such studies are done in the group. Another is the impact of fast voltage fluctuation due to EV charging on light. So this is a EV charging of fast charging. Here you can see when the EV, this is some checks. Before charging, it does some checks. So these checks, so you can see that when these checks occur, there is some voltage drop. Here also when this charger started charging, there is a voltage drop. Here again a check, so voltage drop. And these voltage drop magnitude depends upon the magnitude of the current. If the current magnitude is high, the voltage drop is high. If the magnitude is less, the drop is less. So now what happens is, because of this fast voltage variation, light flickers can come. Light flicker is something what we measure using a term called PST. PST is if the PST value should be less than 1. If it is more than 1, it means that a person, like say if a test sample is there and 50% of the people can see that flicker, so then we say the PST value is more than 1. And usually the PST value is measured for a 10-minute interval. In a 10-minute interval, how many people can see some flicker? So if 50% of the people can see that, then we say the PST value is greater than 1. That is how it is found. So here you can see this was a 30-minute interval. In 30-minute interval, 1, 2, 3 dips were there. So we did like similarly say when we did that measurement in Ting Top, there were some voltage dips seen there also. So we did a probability study that like we took a network of 83 customer network, and we said that if there we saw there are 3 dips occurring in a 30-minute interval. So PST is calculated for a 10-minute interval. So in a 10-minute interval, what is the probability of getting 1 dip? That is 1/3. So based on this probability, we just took that if around 50 cars are charging at the same time in that network, we took a real network and we studied this. So if there are 50 cars charging at the same time, what is the possibility that getting more than 4 steps? When 50 cars are simultaneously charging, what is the possibility of getting more than? That is 100% probability that there will be more than 4 steps. And there is 96 probability that greater than 10 steps. So this steps in real time, an experimentation was done, and the steps was introduced, and the light was and that steps was given to an LED, and with a photo detector, that flicker was measured. So it was found that if there are consecutive voltage dips or non-consecutive, in the sense a 10 minutes interval, consecutively all these dips are occurring, or in the 10-minute interval, they are far occurring. In 10 minutes, maybe in 3 minutes, then around 7 minutes, and maybe in the 10th minute. So such non-consecutive drops. And another thing is we tested it for weak grid, medium grid, and strong grid. The voltage drops was calculated like this. Then around 32 different LEDs of different topologies was tested for both 4 drips consecutively and for 10 drops consecutively as well as non-consecutively. And it was found that LED number 4, like around 32 different topologies. 4 topologies are given here, but other topologies are also there. So the topologies with 4, that was a LED with active power factor filter, where when it was a weak grid, it gave value greater than 1. In the sense, light flicker is surely occurring. And this also 0. 0.7. When they are occurring non-consecutively also in a weak grid, it can give flicker. So we came to a conclusion that flicker due to EV charging depends on number of EVs connected, the topologies of the lamp used, as well as the impedance of the grid. So with this, I'm ending. Actually, we have done a lot of studies there, but because of time, I'm just concluding it. Here is my details. You can just, I'll be putting this in my slide share, so you can just take the PPT from there. And my mail ID is shimi.reggie@gmail.com. So if you have more doubts and all, or if you want to contact me, you can contact. And now, you have any questions? We have around some 10 minutes. We can just discuss. So if anyone is having any questions, I'll stop presenting. I was a little fast because I just wanted at least to cover this portion of some small things. So that's why. So if you have any doubts, you can ask.
Firstly, I must thank Professor Shimi for taking out her precious time, and I guess it might be something around 3 p.m. there.
No. I just in the beginning I said like 2 weeks back I have come here.
Okay.
Yeah, so I am in India now because day after tomorrow I have to join NITTTR. My period is getting over tomorrow. So,
okay. So anyway, so first of all, I'm very thankful to you for taking out your precious time. And now I request the participants, those who have any query, they can ask the questions.
Hello.
Yeah, students, if you have. Yeah, yes,
Good
sir.
evening, ma'am.
Good evening.
My name is Shahrukh, and I'm working on high gain DC topologies
Okay.
for mainly power electronic converters. And I actually want to know that what kind of high gain DC topologies were you using at the time of your research in for charging or in electric vehicles? Can you please
Actually,
comment?
as I already told you, these things like these chargers are already existing chargers. Like many companies like Fuji's, ABB, they have already made their charger, and we took the measurement. We don't know the power electronics inside. Okay, so that's a main problem in these converters. We want to identify what are the problems it is creating. But actually, when we did it, like in NITTTR, we did some topologies. I can just show you the thing. Actually, I didn't go in depth there. So, any like any different topologies. And many a times in research we do a lot of different topologies, but in real world, if you see, when you implement, the main thing is it has to meet all the what to say, standards. That's a very important thing. Oh, sorry. So I think Interleaved boost converters were used. So this was the Interleaved boost converter which we use here at NITTTR. Yeah, this modified. We use Interleaved boost converter with DCN cells, as well as then we modified the Interleaved boost converter, and we tried to implement this Interleaved boost converter, which gave a higher gain and the ripples, because when we use ordinary boost converters, the current ripples were very high. So then we went for modified Interleaved boost converters. We made a prototype and then we tested it here in the EVs. So this was the topology which we tried with Interleaved boost converters with high gain, but many other DC to DC converters are also there. But in the research which I did there, there was like we didn't know what was the like it's yeah, I have removed it. When we did research there, it was a black box. Actually, the chargers are given real time chargers where the in the streets where it is implemented, we just go measure the car thing and then analyze what it is, what problems it is creating. So many a times by seeing it, okay, these harmonics are there, so might be this might be the converter used. Okay, if it's as I told, six pulse converter is used, so fifth and seventh harmonics are hidden. We identify might be such a converter. So we do the backtracking and find out, but we don't know what topologies, because the different companies also they don't share what type of topology they have used. They don't give the details because ABB had installed it there. We had contact with that person, but they were not ready to share those details. So never you will get what converters use there. But yeah, in laboratory we have also developed some converters, many different types of converters with different topologies. Mainly trying to reduce the number of switches. We have come up with a number of different topologies. Boost converters itself, like sometimes buck boost converters, and many are there. So, what type of converter are you working on?
I'm mainly working on non-isolated converters, and
Okay.
I'm trying to shift on coupled converters. Also, you have shown me a couple inductor type topology on an interleaved, and also you have used a voltage multiplier to increase the gain. I can
Yeah,
see from your topology,
yeah,
and
yeah.
which will reduce the voltage stress on semiconductor devices. Also, of
Yeah.
course, the interleave converter reduces ripple, which reduces size and cost.
Yeah, interleaved.
So,
Mainly, first we did with an ordinary converter, and only we did. So the problem was current ripple, very high current ripple. Then we went for the interleaved. In interleaved also we found like we couldn't get the gain what we required because we had a 48-volt battery for the auto rickshaw which we designed. So then we did modified that with number of cells we increased to get our level, and in that case we found that the ripple. So it depends, like might be when we went for manufacturers saying that this is a good model, but they were not ready to accept it, bro. Since they require number of many other things, like what type of switching frequencies we are using, it has to uh, get with the limits, like all the THD and other limits, and many other problems are also there. So yeah, we have to work on it and come with a very good model. Then industries will, you can patent it, so industries will accept, because we went for one model, we patented it with a boost converter only with reduced number of switches. We had some like very good levels achieved with that, so we had given it for patent. So if you come out with good models, you can go for patenting, and then you can like approach some companies for making like for technology transfer. So that will be a good thing. So you can just try to modify your work, improve it. Nice to
okay,
know that you are
thank you,
working
ma'am.
on it.
Thank you, ma'am, for clearing my doubt. And actually, I'm working under Dr. Muhammad Tariq and Dr. Muhammad Zaid, sir, in my research work, and they are helping me a lot. And also, I'm trying to build my topologies on Typhoon HIL, but it is very challenging for me to work on a Typhoon HIL because simulation is not easy as MATLAB
Yeah.
on Typhoon HIL. So to
But you
so
have
we
good
are
support. You
these
have
days we are
Satnam and many other
labs are
people
going.
who are there to support you. And they have all the power converters and many other like component level also they have it. So you have to just contact with them. And in case if you want a particular type of cells like or the devices according to what you have got it from the market, you can tell them, they will tune it for you, like they will give you the circuit accordingly, then only it is possible. I do know that it is little difficult.
Yes, ma'am.
Thank you, Sharif, for putting your query. So, is there any other query? So, I think most of the things are clear to the participants. So, once again, I thank Professor Shimi for giving such a nice presentation on EV and other power quality issues associated with it. And yeah, and this actually this is a very pertinent issue nowadays, because government of India is also planning to have a lot of EV penetration in the car segment. So definitely, whatever the challenges you have presented, these they may come in future as well in the Indian market.
Yeah.
So once again, very thanks
Yeah.
for your nice presentation,
Thank
and
you, sir. Thank
and
you for inviting me and
Uh,
giving
and,
me an
and,
opportunity.
I'm also thankful to the participant for their time and for the patience hearing. Thank you. And
Yeah,
with
thank
this,
you.
we end the session.
Okay. Thank you, sir. Thank you.